The assembly pipeline at BV-BRC, I think, is one of the achievements that we have that makes things truly easier for researchers. And I'm going to show you all those pieces so you can see how it works. Generally, what assembly means is you're taking sequencing reads and you're creating contigs. Now, these contigs could be a genome, but it could be multiple genomes if it's from a metagenomic sample. We're going to use the same sample data through all of these lessons, and it's taking it from this particular study, which was by Street et al. And this was the study where they had people who had a bacterial infection following an orthotic replacement, like a hip or a knee or a shoulder. And it's serious when you get those kind of infections. They have to remove the device and treat you because the bacteria are sort of sheltered around the device and the immune system can't get to them. So it's a pretty horrible thing to happen to somebody, but they collected a lot of samples from these people, and we're going to use one of them. So this is the pipeline at BV-BRC. And you'll notice that there are a lot of steps in here and a lot of different algorithms in here. If you're a bioinformatician and you want to string all these things together to do this, go ahead. That's great. Do it. But if you are a research biologist who does not have the skill to do this, or you're a bioinformatician and you don't want to take the time to do it when you can just use it at BV-BRC, welcome. Come in. We'd love to have you use it. So the steps involve trimming, normalizing the data. Now you may be thinking, what is normalizing the data? Sometimes you have areas where a part of the genome or an area of a contig has really dense reads attached to it, and other parts are very sparse. Sometimes this will cause an assembler to fail. So when we have normalizing turned on, that it will take off some of the weight from the dense parts. This doesn't mean that the coverage becomes low. I've seen coverage at like 160% depth. So it doesn't mean that, but it's just trying to equalize it. It never does anything to the sparse areas. It brings down the number of reads where it's really densely populated. And this also makes the assembly go faster. You can see we have a number of different assembly algorithms. And then you can, if you wish, you can stop at the assembly, or you can go into polishing. And what polishing does is once you have your assembly, there are areas where there are discrepancies that the assembler couldn't decide on it. So it'll do another round, a polishing round, and it'll try to map the reads in and see if it can resolve those differences. And we have two different types of polishers depending on if you have long or short reads and different aligners within that. So let's talk about the different assembly pipelines. Spades and Unicycler are primarily short read assemblers. So you can use them for like your Illumina reads, either single or paired. Now, Unicycler can be used for a hybrid assembly. So what that means is if you have long and short reads, and if you can pay for that, those make beautiful genomes. So I would encourage you to do that. It gives you many fewer contigs. But anyhow, if you choose Unicycler for a hybrid assembly, what it first does is starts with the short reads and starts generating a scaffold, but then it brings in the long reads, and it's bringing the short read scaffolds to the long read to try to get a nice assembly. Canoe and Fly are long read assemblers like PacBio or Oxford Nanopore. Now, both of these can also be used for hybrid assemblies. But in this case, they start with those long reads and then map the short reads onto them. We also have Metaspades, which you can use to assemble metagenomic data, plasmid spades, which is trying to pull a plasmid out of a more complex mixture of data, and MDA. and that's a specialized assembly pipeline for single cell data. There are other additional assembly algorithms. For the trimming, we use trim galore. For the normalization, we use BB norm. Now, if you're going to do polishing, if you have long reads, we use Racon, and actually we also use Minimap 2, which maps the reads to the genome for Racon. If you're going to do short read polishing, we use Pylon, and that also uses Bowtie 2, which maps the reads to the genome, and SAM tools, which converts a SAM file to a BAM file. So those are all part of the Pylon. Now, after all the assembly is finished, we also have some ways to visualize it and to look at the quality. We run a pipeline called QUAST, or an algorithm called QUAST, which evaluates and gives you statistics on your genome. And then we have a nice little visualization for it, as long as the contexts are not in the thousands. And that's called Bandage, which is short for Bioinformatics Application for Navigating De Novo Assembly Graphs Easily. It just generates a genome graphic. So this is what the landing page looks like for the genome assembly. And you'll be taking the reads, the short reads, paired short reads, or single reads, and then you move them over here into the selected libraries box. And you can put in as many as you want. Like sometimes when you are having a genome sequence, they run it on 4 lanes in case something fails. And often, if everything worked well, you'll have 4 read files for each of those cells on the sequencing gel. You could use all of them here, but if it gets to be too big, if we're talking gigabytes, if it's too much data, the assembly pipelines are set to run for a certain amount of time, and you run the risk of failure. But you don't know unless you try, and then if it fails, just send us a ticket and we'll try to reset it with more time. So one thing I want you to be aware of, because I find that a lot of people don't know about what kinds of things that you use to generate an assembly. The files have to be tagged as reads. And we put in here that reads must be in FASTA or FASTQ format, typically ending in .fa, .fasta, .fq, or .fastq. And we also accept zipped files, so they can have the zip notice on them too, ending in GZ. You can change the tags from your workspace. And I've had people actually have pictures of gels that they have tagged as a FASTA file, and they didn't know why their assembly failed because it was a FASTA file from their perspective. So I want to show you what read files look like so we don't have to have these difficult conversations later on. These are FASTQ files. They're 4 lines. The first line always begins with this @ and then it begins with a sequence identifier. And none of this means anything to me, but it's all here. The second is the raw sequence for that, and they're in letters. The third begins with a plus, and sometimes there can be other descriptions in there. So they say, I've never seen anything but that. And then this fourth line, which is kind of weird when you look at it, this is the quality sequence for each of these. For everything in the sequence, it's going to have a quality score for each of those. And each of those lines mean something. The A's and the E's tell you something about how good that particular sequence is. So that's the FASTQ file. The FASTA file is a little easier. The first line always begins with this little greater than sign. And it's got information here, and generally it'll say something that indicates to you that it's a read file, like forward or reverse or something like that. Because for those of you who know, a config file looks a lot like this too. It starts with an identifier and then it's got the sequence that can span multiple lines. And you see this for a lot of those long reads. And so that's basically it. You know about the read files you need. You know how the assembly pipeline works. So let's get started submitting some jobs and look at what we get. See you in the next one.